Hello, this is 17th lecture for our linear algebra series. We will discuss positive rate operators and isometries today. Recall that last time we have spectral theorem, and spectral theorem just characterizes nice operators. So when we say nice operator, these are operators which can be expressed as a diagonal matrix with respect to some orthonormal bases. And these nice operators, when our setting is the complex vector space, is just those normal operators. And when we are in the real vector space, we have the self-adjoint operators. Today, we will start with positive operators. We will begin by a definition. Let us define what a positive operator is. So an operator T in our vector space V is positive if your T here is self-adjoint and also your inner product TV is none greater than or equal to 0 for all our vector V in the vector space, inner product space V. Okay. Example of positive operators are the following. If U is a subspace of our V, then the projection of U is positive. And number two, if we get our T and also self-adjoint, and we have say the previous example, our BC are element of R such that your B squared is less than 4C. Then your polynomial operator, this operator defined this way, T squared plus BT plus C times I is positive 2. As we have shown in the proof of our previous result, stating the characterization of self-adjoint as an of quadratic operators. I mean, in use in the proof of self-adjoint operators having eigenvalues. All right. Okay, let us now define another operator, another type of operator. Say R, an operator, is called our square root of an operator T if they are squared is equal to T. To illustrate this, let us consider the example T, which is an element of an operator, say in F3, and then we define T as T of x1. Let us consider, let's use the letter Z. Z1, Z2, Z3 is just Z3 and then the other one components vanish. And let us also consider R and F3 and then define R as follows. Z1, Z2, Z3. It's just Z2 and then Z3. And then the third component will be 0. This is the claim is R is square root of our T. Of course, if you apply T twice, then if you get this, and then okay, R of Z1, Z2, Z3. Just R of Z2, Z3, 0. And then this is just this will become Z3, and then 0, 0. Okay. Okay. Of course, this is just for example here, this is Z2, Z3. So this part here will go when transferred to this part, here. So this is our new input. And then here, this will go here, and then this will go here. So here it is now, and then this is I'm gonna take a pause, and then you realize that what's going on here. So I have put in the arrows. Okay. So now we will characterize our positive operators. So notice that if we get a complex number, then the complex number is non-negative if and only if it has a non-negative square root corresponding to the following relations that we will show. So I would like to remark that positive operators correspond to numbers 0 to positive infinity. So better terminology would be to use the non-negative instead of positive. However, operator theories already get accustomed to call these things as a positive operators. So anyway, just some notes on convention. So here we will characterize, this is a theorem, characterization of positive operators. And then we will prove some of them. So let us first have let our T be an operator. Then the following are equivalent. A, T is positive. B, we have T is self-adjoint, and all the eigenvalues are non-negative. Of course, eigenvalues of T. And then letter C, T has a positive square root. This is square root. And then D, T is has self-adjoint square root. And letter E, there exists an operator R, of course, such that your T is expressed as the product of the adjoint of R with R. And then let us present the proof. We will prove it this way. A implies B, implies C, implies D, implies E, and then back to A. The arrow is not. All right, let's begin the proof. The proof here is somewhat sketchy, so Suppose uh, suppose A holds, then what can you say? That is T is positive. So T is positive. By definition, T is self-adjoint from the definition of positive operator here. Positive is self-adjoint. And what can you say about the self-adjoint operator? Then let lambda be an eigenvalue of our T. Corresponding to the eigenvector V. Okay. Then your T, the inner product, this inner product is greater than 0. And then T of V is just lambda V, because lambda is an eigenvalue V. Then you can put the lambda out. This is VV. And then you can have a lambda and then this okay. This one here is ln here, and the conclusion is thus your lambda is non-negative because of this relation here. So that implies okay, now that's up adjoint, and then the eigenvalues are non-negative, which is what we want to show, letter B. Now suppose that B, then what can you say about the uh, self-adjoint and all the values are negative? And we will invoke the spectral theorem. So by our spectral theorem, there exists E1 to En orthonormal basis of V, and then these orthonormal bases are consisting of eigenvectors, of our linear map T. Okay. Let us let lambda 1 to lambda n be the corresponding eigenvalues. Then what can you say? We can say that each lambda sub j is non-negative. Let us consider a linear map R such that your R of sub j is just square root of lambda sub j E sub j. This is for all j from 1 up to n. Here, R is a positive operator, positive, and I claim that this is a positive operator. I will leave it as a verification, right? It's that so. And then you have R squared of E sub j is just lambda j E sub j. This is just equal to t e sub j. This is for each t. For each j. Okay, let me. For each j, which implies that r squared is equal to t, which is what you want to show. So C holds. Now we want to show C implies D. So C implies D. So what is C? C is has a positive square root, and then T has T has a positive square root, and T has a self-adjoint operator. It's just by definition. By definition of our, because we have, if our positive operator, every positive operator is self-adjoint. Now, suppose D holds. Okay. And then what is D? D has a sub-adjoint square root. So there exists an R such that our D is R squared. And then this R here is self-adjoint. Okay. Then if you have T, this is just R star R. This because being self-adjoint, we get T star is just equal to this. And then what does we prove? Thus, we have our E. Suppose now we have E holds. We need to prove A. Note that our TV V is equal to R star of V. And then we know that our R star here is T is self-adjoint. Then we have this claim. And then, of course, we can express this way. And, of course, this is greater than or is equal to 0. This is for every V in our inner product space V. Thus, your T is positive, completing the proof of our characterization for positive operators. Okay, let me claim the following remark. Let me have as a following remarks. So each non-negative number has a unique non-negative square root, and then the next result will be will have almost the same property. So the theorem is as follows. Every positive operator on our vector space B has a unique square root. Well, I prove this. I think this is a relatively long proof, but okay, let's prove this. The proof is involved, like very, quite long. Suppose that T here is positive, and then and v eigenvector of our t with respect to lambda greater than 0. This is the consequence of being a positive operator. So your t of v is lambda v. Let r be the square root of t. We want to show that r of v is square root of lambda times v. This will imply that the behavior of r on eigenvectors of b is uniquely determined, and because there is a basis of b consisting of eigenvectors of t, this will imply that r is uniquely determined. So here we will prove that r of v is this one. So by spectral theorem, there exists our orthonormal basis of v, then of eigenvectors of our operator t. Operator not t but operator r. R is positive by our characterization earlier. All its eigenvalues are non-negative, greater than or equal to 0. Thus, there exists non-negative lambda sub 1 up to lambda sub n, such that your r of ej is square root of lambda j e sub j. This is for all j above. So ej, this one is an orthonormal basis. We can write our vector in vector space as follows. So v is just linear combination of the orthonormal basis elements. And then, of course, these AI are field elements. Thus, your R of V is just A1 square root of lambda 1 E1 plus AN square root of lambda N EN. And also, if you operate twice, you get A1 and then lambda 1 E1 up to AN lambda N EN. We know that our R squared is equal to T, and your T of V is lambda V. You get the equation. We have our A1 E1 lambda E1 up to AN lambda EN lambda N EN is equal to A1 lambda 1 E1 plus AN lambda N EN. That means that we get A sub j lambda minus lambda j is equal to 0 for j from 1 to n. Here, we don't have this this is for this part here. And this part here is this part. Okay. That means that your V is just summation of A, J, E, J. And then J here is, well, lambda J is equal to lambda. Thus, your RV is just sum of A J square root of this and then E sub J, which means this is just equal to square root of lambda V. This happens when our J such that your lambda J is equal to lambda. This is what we want to show. What we want to show here is the following, this, and then we already have this one, J such that. So J is lambda. Okay, we will do the same kind of thing with isometries. Let's define an isometry. Say S is called an isometry if your for all V in inner product space. And then this is, in other words, isometry preserves our norms. And then, of course, lambda I is an isometry whenever lambda is in F. Satisfies the absolute value of lambda is 1. And then we will provide non-trivial example here, which we will use in the proof later. Suppose lambda 1, lambda n scalars with absolute value 1. So they are 1 or negative 1. And we get a linear operator S satisfying the following. S of Ej is lambda J Ej. And then we have with for A1 to Ej orthonormal basis of V. And then the claim here is S is an isometry. So the proof, let V be our element in the vector space, then express V because V is just here V E1 up to the inner product of V and En N. And your magnitude of V squared is just the magnitude of each component V. This is used in our proof before. And here, if we apply our S to V, you get V E1 S E1 up to V En S En. And this is just equal to V E1 lambda E1 up to V En lambda En. And then if your lambda, recall lambda sub j is magnitude 1, then no, that is true. Then the magnitude of, or the norm of SV squared is just this. Basically, because of this one, thus your SV is just the norm of our V. That means S is an isometry. And then we will provide characterization for isometry. Um, S in S is an isometry. B, we get S of U, S of V. It's just UV for all U and V in our vector space P. S of E1 up to S of En. S of En, this is orthonormal for every orthonormal list of vectors in our V. And then letter D, there exists orthonormal bases E1, En of V, such that S of E1 up to S of En is orthonormal. And our E here is the following, and F is almost the same. And if you get S an isometry, S star is also isometry. And H here, S is invertible. And the inverse is just the adjoint, given that S is an isometry. Okay. Now, I will leave this proof as exercise and say something about isometries on complex vector space. For F equal to C, S is isometry if and only if there exists an orthonormal basis of V consisting of eigenvectors. Eigenvectors of S whose corresponding eigenvalues all have the absolute value 1. I will prove this, and this is the proof is B implies A is via our example earlier. then A A implies B. This is our proof. Suppose S is isometry, then by complex spectral theorem, there exists our orthonormal basis consisting of eigenvectors of our S. Now for J, in this set, let us have lambda sub J, the corresponding eigenvalue of T sub J. Then the magnitude of lambda sub J is equal to the norm of lambda sub J sub J, which is just equal to S of T sub J by our earlier claim. And this is equal to the E sub J, which is just 1. Thus, your eigenvalue has magnitude 1, and then this is completing the proof. So this is a symmetry, then the absolute value is absolute value of each eigenvalue is 1, and then suppose the absolute value and eigenvalue is 1, then S is a symmetry by the example that we have earlier. Where is that? This is the example that we have. This one. Let's go back to our last claim. I think we're done for today. Next meeting we will discuss the of course we will continue with polar decomposition, and singular value decomposition. So what are these? What are these things? So polar decomposition, we can relate this to the existence of an isometry such that this isometry has a nice presentation, which is just in terms of the square root of an operator. Yeah, and then for polar singular value decomposition, this is just we will describe every operator on the vector space V, and then in terms of its singular values. And then, of course, we will first define what a singular value is. Basically, they are singular values are eigenvalues of this special kind of square root operator. Square root of some operator multiplied with each adjoint. We will have more of that next time. So I think I'll end here. See you.